We live in a minor spur between major arms. Our solar system doesn't lie in one of the Milky Way's grand spiral arms. Instead, we occupy a small structure called the Orion Spur, a relatively quiet lane of stars nestled between the larger Sagittarius and Perseus's arms. It's not especially dense, nor especially active, but that may be why we're here. In the calm between galactic highways, massive supernovae are rarer. Radiation storms less frequent. This quiet corner may have given life on Earth the time it needed to emerge and evolve. From the outskirts, the galaxy seems dramatic and radiant. But in this quiet spur, we found just enough peace for complexity to unfold. The Milky Way has a bar-shaped center. When astronomers look toward the galactic core in infrared light, they see not a perfect circle, but a thick elongated bar of stars crossing the middle, a kind of glowing bridge. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. Bars like this are common in spiral galaxies. They form when stars in the disk begin to drift inward and pile up along a central axis. Over time, the bar becomes a stable structure, stirring gas, triggering new stars and feeding material toward the black hole at the center. It is not just a shape, but a dynamic engine, sculpting the galaxy's heart from within. It's part of a larger structure called the local group. The Milky Way doesn't exist in isolation. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster drifting together through space. The two largest members are the Milky Way and Andromeda, each with its own family of satellite galaxies. Scattered around them are smaller dwarfs, faint ellipticals, and star-poor galaxies made almost entirely of dark matter. The local group spans more than 10 million light-years and it is bound together not by proximity alone but by gravity. We are part of the family quiet, widely spaced but still linked by the invisible threads of shared motion and mutual pull. Galaxies in the local group are gravitationally bound. Despite their vast separations, the galaxies of the local group are not drifting apart. In fact, many are moving slowly toward one another. Gravity holds them in a kind of slow-motion ballet, curving their paths across millions of years. Some of the smallest galaxies orbit the Milky Way like moons, looping and falling, dissolving into streams. Others drift independently, but remain tethered, caught in a web of shared motion. Over time, this group may condense. Galaxies may merge, fade, or be absorbed. It's not a static arrangement, but a gentle gathering of cosmic islands, a family drawn closer by time, inertia, and the long reach of gravity. The galaxy's disk has a thick and thin component. The Milky Way's disk looks flat from a distance, but up close, it's layered. The thin disk is where we live. A wide, dense plain filled with young stars, open clusters, and star-forming gas. But above and below it lies the thick disk, older, puffier, and more diffuse. Stars in the thick disk tend to be older with fewer heavy elements. They move in orbits that are more tilted and elliptical, suggesting they formed under different conditions or were stirred by early galactic collisions. The galaxy's disk is not uniform. It's textured, layered, and shaped by time, like sediment settled on the floor of a cosmic ocean. The galaxy's magnetic field threads through the disk. Though invisible to the eye, the Milky Way is laced with a vast magnetic field stretching across the disk, rising into the halo and weaving through the interstellar medium. This field is weak by earthly standards, but over galactic distances, it shapes how cosmic rays travel, how gas clouds collapse, and how matter flows through space. The Milky Way is not perfectly balanced. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is lopsided. Even the star counts between hemispheres are slightly off. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living things, carry traces of their histories in their shapes, scars of collisions, wrinkles of time, and quirks of uneven growth that give them character and depth. The oldest known star may live in our halo. High above the galactic plane, Drifting through the halo, astronomers discovered a star that may be nearly as old as the universe itself. It contains almost no heavy elements, a signature of stars born soon after the Big Bang before generations of supernovae enriched the cosmos. It likely formed over 13 billion years ago, long before the Milky Way was fully formed. It burns quietly now with a soft red glow, low in mass but rich in history. It is not just a star. It is a time capsule, a living relic from the universe's earliest dawn. The center of the galaxy spins faster than the outskirts in the inner regions of the Milky Way. Stars orbit the center much more rapidly than those farther out. Near the core, the gravitational pull is stronger, packed with mass from stars, dust, and the supermassive black hole Sagittarius A*. This causes stars to sweep through tighter, faster orbits, completing revolutions in just a few million years. Out in the suburbs of the galaxy, like where our sun lives, stars orbit more slowly, taking hundreds of millions of years. This uneven rotation creates twisting patterns, stretches spiral arms, and keeps the disk from behaving like a solid structure. The galaxy moves like a great wheel, but one whose rim lags behind its core. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not fixed trails of stars. They are patterns formed by waves of higher density moving through the galactic disk. As gas and dust pass through these waves, they are compressed, triggering star formation and lighting up the arms with bright young stars. These stars eventually drift out of the wave while new ones form behind them, creating a self-sustaining illusion of structure. Like ripples in a pond or traffic comping on a highway, the arms are dynamic, always in motion. From a distance, they appear still. From within, they are a dance of matter and rhythm, shaped by gravity and time. Stars are born from cold collapsing gas. In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light-year wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly takes hold. Small regions grow denser and begin to collapse under their own weight. As the gas falls inward, it heats, spins, and flattens, forming a protor at the center. Over time, the pressure and temperature grow until nuclear fusion ignites, and a new star is born. From the coldest shadows come the brightest lights, spun gently into being by the quiet force of gravity. Star clusters can dissolve into the galactic field. Many stars are born not in isolation but in groups. Tight clusters formed from the same collapsing gas cloud. These clusters bound by mutual gravity drift together for millions or even billions of years. But over time they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away one by one until the cluster fades into the general starfield of the galaxy. Even our sun was like a born in a stellar cluster long ago. Its siblings now scattered, dimmed, or lost in the haze of distance. The galaxy contains ancient hypermetal-poor stars. Among the rarest and most precious objects in the Milky Way are hypermetal-poor stars. Stars whose atmospheres contain almost no elements heavier than helium. Some of these contain less than 110,000th the iron found in the Sun. These stars are believed to be among the first born after the very first supernova, carrying only faint traces of enrichment from a universe still forming itself. They are incredibly old, incredibly pure, and scattered in the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing, gravitationally bound signature from a near-forgotten epoch. Planetary systems form throughout the Milky Way. Planets are not a rare feature of the cosmos. They are a natural consequence of star formation. As a new star ignites, a rotating disk of leftover gas and dust surrounds it. Within this disk, particles stick together, gather mass, and grow into worlds. Across the Milky Way, planetary systems are common. Some are vast with gas giants and frozen moons. Others are compact with rocky planets hugging close to dim stars. Some may resemble our own while others defy our expectations entirely. The galaxy is not just full of stars. It is full of systems, solar families, each one with its own unique balance, orbit, and potential. Earth is near the corotation radius. In the Milky Way, the spiral arms rotate at a different speed than individual stars, like a moving pattern rather than a solid structure. But there is a special distance from the center called the corotation radius, where the average speed of stars matches the rotation speed of the spiral arms themselves. Earth's Sun orbits close to this boundary. This gentle match in motion may help us avoid frequent crossings of spiral arms, places with higher star density, more supernovae, and gravitational disturbances. We live quite possibly in a more stable neighborhood of the galaxy, shielded not by walls, but by resonance. The Sun bobs up and down through the galactic plane. As it orbits the Milky Way, the Sun doesn't follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork in slow motion, rising and falling over tens of millions of years. This vertical oscillation is caused by the gravitational tug of the galaxy's mass, pulling and releasing the solar system as it moves. Some researchers have even wondered whether this motion might influence cycles of extinction on Earth, though the evidence is not yet clear. Still, it's a reminder. Even on its steady path around the center, the Sun is not gliding. It's swaying softly through space. We don't know what dark matter is, but we know it's there. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly. It does not emit or absorb light. It passes through ordinary matter as if it weren't there. But its gravitational effects are unmistakable. It holds the galaxy together, explains the unexpected rotation speeds of stars, and shapes the formation of large-scale cosmic structures. Without it, the Milky Way would fly apart. Astronomers detect it not by seeing it, but by watching how it moves other things. It is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest mysteries in science. There's more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat luminous disk, but the majority of its mass resides elsewhere. The galaxy is surrounded by an enormous dark matter halo extending far beyond the furthest stars. This halo holds the galaxy together, outweighing the disk by a large margin. It is populated sparsely with ancient stars and globular clusters, but its true bulk is unseen. When we think of the Milky Way, we picture its spiral arms and starry plane. But that's only the glowing surface. The mass that defines the galaxy, its gravity, its motion, its reach is mostly hidden, enveloping everything like a quiet shroud. The Milky Way's core may have flared as a quasar. Today, the heart of our galaxy appears quiet, but there is evidence that it was once dramatically more active. The presence of huge gamma-ray structures like the Fermi bubbles and traces of high-energy light reflected in surrounding clouds suggest that the supermassive black hole at the center may have once flared as a quasar, a brilliant violent beacon fueled by infilling matter. Quasars are among the brightest objects in the universe, outshining entire galaxies. If the Milky Way once burned like this, it would have looked dramatically different, a spiral wrapped around a blinding heart of light. That time has passed, but the echoes remain. The galaxy's structure changes over billions of years. Galaxies may look timeless, but they are always evolving. Spiral arms shift. Bars form and dissolve. Gas flows inward and outward. Stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and lopsided, is slowly altering. Encounters with dwarf galaxies and dark matter can bend or twist the structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is not the one that was and not the one that will be. Its beauty lies not in permanence, but in quiet transformation. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide, black holes spiral together, neutron stars crash, and entire galaxies merge. These events send out gravitational waves, ripples in the fabric of spacetime itself. Though faint, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel. They are incredibly difficult to detect, but observatories like LIGO and Virgo have already captured several. New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, as you rest, space itself is shifting. Not enough to feel, but enough to tell us that somewhere far away, the universe is changing. Some stars orbit in elongated tilted paths. Not all stars move in neat circles around the galactic center. Some follow long stretched ellipses, their paths looping high above and far below the disk, tilted at odd angles from the main plane. These stars likely come from different origins. Relics of dwarf galaxies swallowed by the Milky Way or survivors of ancient gravitational upheavals. Their orbits are clues, three-dimensional maps of the galaxy's chaotic past. By tracing their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems, tilted, stretched, but still bound to the whole. The Milky Way emits neutrinos we can barely detect every second. Trillions of neutrinos pass through your body, straight from the stars. These ghostly particles are produced in nuclear reactions from the sun, from supernovae, and from cosmic rays striking atoms in space. The Milky Way is bathed in them. Yet they are so light, so unreactive that they slip through almost everything, leaving no trace. Special observatories buried deep underground or under ice try to catch just a few flashes of light from a rare collision. Neutrinos carry information from places we cannot see, from stellar cores, collapsing giants, and the galaxy's unseen energy. They are the whispers of cosmic fire. Interstellar space isn't empty. It's a turbulent sea. Between the stars, space is not smooth or still. The interstellar medium, thin clouds of gas and dust, is stirred by shock waves, magnetic fields, and the motion of stars. Temperature can vary wildly. Flows of material collide, mix, and fragment. Clouds stretch, fold, and tumble. On large scales, this creates a kind of turbulence like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are all affected by this restless sea. What looks from afar like calm starlight is up close a dynamic, rippling fabric, shaped by invisible winds and ancient energy. The galactic halo may contain rogue planets. Planets are not always tethered to stars. Some form normally and are later ejected from their systems. Others may never have had a star at all. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though difficult to detect, studies suggest that there may be billions of them in the Milky Way, some even in the outer halo, where stars are few and far between. Without light or warmth, they float unseen. Warmed only by internal heat, they are orphans of the galaxy, planetary drifters following long, lonely paths through the darkness between stars. Magnetic fields shape the flow of cosmic dust. Interstellar dust, tiny grains of carbon and silicate, moves not just under gravity, but also under the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave light. In others, they align with magnetic lines, polarizing the starlight that passes through them. Understanding these effects helps astronomers trace the magnetic field structure and even remove its influence from cosmic background studies. Dust is not passive. It dances to a magnetic rhythm, following hidden patterns in the dark. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a kilonova. In this brief blinding explosion, enormous quantities of heavy elements are forged. Gold, platinum, uranium, and more. These materials are cast into space, mixing with gas and eventually forming new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from such collisions. They are not just luminous bodies, but record keepers of ancient cataclysms burning with the residue of stellar wreckage and cosmic alchemy. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies a bar of stars, an elongated bridge of light crossing the central bulge. But deep within that bar, astronomers have found hints of another smaller bar tilted at a different angle, rotating independently. This inner structure is difficult to see directly, obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. Bars like this may help funnel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The Milky Way's center is not one simple shape. It's a layered shifting labyrinth of light and motion. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system. It draws in fresh gas from the intergalactic medium. Long tenuous streams flowing through the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter, shock-heated forms, lighting up in ultraviolet or X-ray light. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos. Hot gas bubbles form chimneys out of the disk. When clusters of massive stars go supernova, they create enormous cavities in the interstellar medium. These can join together into superb bubbles, vast pockets of hot gas that punch upward through the galactic disk and vent into the halo. The result is a kind of chimney, a channel where energy, gas, and magnetic fields escape from the plane of the galaxy. These chimneys regulate the pressure of the interstellar medium, redistribute metals, and help shape the halo structure. The galaxy in this way breathes not just within the disk, but through towering columns that carry its energy up and out into the dark. The galaxy shines in X-rays from old stars and black holes. Though the Milky Way appears calm in visible light, it glows fiercely in other wavelengths. X-rays pour from its core, from collapsed stars, and from the edges of black holes. White dwarfs and neutron stars in binary systems can siphon matter from companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton. We cannot see this high-energy light with our eyes. But telescopes like Chandra and XMM Newton paint a very different portrait of the galaxy. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning, fast and precise, with beams of radiation sweeping across space. These are pulsars, and some rotate hundreds of times per second, pulsing in regular measurable rhythms. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink quietly, remnants of death, but also beacons of astonishing order. They keep time not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in visible light, hidden by dust, distance, or faintness. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Using arrays of radio telescopes, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in darkness. Where light is blocked, radio soundings let us see. The galaxy speaks in a language we can't hear, but one that science has learned to translate into shape and shadow. The Sun was likely born in a stellar cluster. Stars rarely form in solitude. They are usually born in groups, stellar clusters shaped from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of these. Long ago, it shared space with hundreds, perhaps thousands of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the motion of the galaxies scattered the cluster. Most of the Sun's siblings have wandered far, flung into different orbits, carrying with them frights of our shared past. Some may still shine nearby, invisible among the stars, lost family in a sea of light. The Sun's siblings are scattered across the galaxy. Though the Sun's birth cluster has long since dissolved, astronomers are searching for its lost siblings, stars that share its age, motion, and chemical fingerprint. Using vast surveys like Gaia and spectroscopic databases, researchers hope to identify these long-lost relatives. A few candidates have emerged. Stars that may have shared our origin formed from the same cloud of enriched gas. If found, they could reveal details about the conditions in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient kin may still shine. The galactic disk wobbles as it spins. The Milky Way's disk is not perfectly flat. It wobbles, gently, rippling like a spinning plate nudged off balance. This warp is most visible in the outer regions where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly like a vast wave moving through the stars. From Earth, we don't feel it. But from afar, the Milky Way is not a pristine spiral. It is a breathing, undulating sheet of stars, curving gently as it turns. Galactic tides can distort star clusters and streams. Just as the Moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters. Clusters in the process are being unraveled. Galaxies slowly torn apart. The galaxy doesn't break these structures suddenly. It unravels them patiently, strand by strand over millions of years. The Milky Way's mass is still uncertain. You might think we would know the mass of our own galaxy, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast dark matter halo, which we cannot see directly. Estimates vary. Some suggest a mass close to 1 trillion times that of the Sun. Others place it much higher. The uncertainty comes from trying to measure how fast stars orbit at great distances, a task clouded by limited data and the influence of invisible matter. The Milky Way is our home, but its weight remains a quiet mystery. It may be heavier than Andromeda. For many years, astronomers assumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. But recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that's true, our galaxy could outweigh Andromeda despite its more modest appearance. This matters not only for comparisons, but for predictions. When the two galaxies eventually merge, their relative masses will shape the encounter's dynamics. The Milky Way may look gentle, but beneath its quiet spiral arms, it carries more weight than we once imagined. The Melanic clouds may be on their first orbit. The large and small Melanic clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way. But new evidence suggests they may be newcomers captured only recently in cosmic terms. Their velocity and motion through space hint that this could be their first close pass. If true, they're not long-standing companions, but distant wanderers just now falling under the Milky Way's pull. Their arrival has stirred the outer disk and warped the galaxy's shape. As if the Milky Way is responding to a new gravitational guest, the sky quiet is full of first encounters. The melanic stream is a ribbon of stripped gas. Trailing behind the melanic clouds is a vast ribbon of hydrogen gas. A structure called the melanic stream. It stretches over hundreds of thousands of light-years wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces as the dwarf galaxies passed close to one another and to the Milky Way. Invisible light, it reveals itself in radio wavelengths, a long trailing whisper of motion and loss. The stream may one day feed new star formation in the Milky Way or settle into the halo like a thread of memory stretching between galaxies. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas and even some stars move in highly inclined orbits, passing above and below the galaxy's main structure. These polar orbits likely come from past mergers when dwarf galaxies or stray clouds were captured at odd angles. Over time, they continued to orbit on tilted paths like comets around a planet. These misaligned orbits are records of disruption. Visible reminders that the galaxy is not a closed system, but an evolving structure shaped by the unpredictable flow of cosmic history. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light-years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. Over time, the expansion slows, but the shells remain. Ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks, still echoing in the cold. Stars occasionally collide in dense regions. Space is vast and stars are small. But in the densest regions of the Milky Way, such as the cores of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic. A burst of light, the merging of two suns, or the formation of a rare blue straggler star, one that appears younger than its neighbors. These collisions are rare, but not impossible. Over billions of years, the tightest stellar neighborhoods can rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently, and space is never quite empty. Binary stars can be torn apart by tidal forces. Many stars live in pairs, orbiting each other in gravitational embrace. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole or through a dense cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star, speeding through intergalactic space. These stellar breakups happen silently in places we rarely see, a quiet tearing of ancient partnerships by gravities in different hand. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, but occasionally a star reaches escape velocity over 500 km per second and is flung outward, never to return.